look at what I say, the legacy plants, the existing large-scale reactors, you know, anything, stuff that was built through the 70s, 80s, and some were even finished as late as the 90s, some plants that have been started and then stopped somewhere along construction. Those plants are in the, you know, tens of, high billions to tens of billions range to build a single plant. And which is okay to do, but the return on investment over that is, you know, 30 years plus. So that's a tough thing for a company to take on that kind of corporate risk and say, we're going to build this plant and spend, you know, do an outlay of 10, 15 billion dollars. So that's probably financially is the biggest risk, or I'll say what's holding us back right now from building new nuclear. Small modular reactors, you're starting to hear more talk about that. You may have heard that technology is still developing. There's only a few designs right now that are approved by the NRC for construction. You'll see that change, but I think this country's probably still a decade from having a small modular reactor built and in service. Our company has officially, I guess, gone on record saying we're exploring new nuclear. If we build, though, it will be in Virginia, and already it would most likely be our North Anna site, which is in central Virginia. It was already, work had been done about a decade ago looking to build another reactor there. So there's already been legwork done with the Nuclear Regulatory Commission. There's already some early site permits and things in place, so it would make sense for us to build there first as a company.
Just on a technical level, if this current site here at Millstone were to expand, would the existing transmission lines coming from here also need to be expanded, or can the existing transmission lines handle the added capacity?
That I don't know.
I think that they would need to be expanded, and they are owned by Eversource, the transmission. So I think the transmission in the entire state needs some upgrades,
yeah. But
certainly that would be part of that.
The reactor is there. All the site, the power would make goes out through a couple lines here to our switch yard, and then you can see this kind of paved or mode area is the lines going out for distribution. So we have four major 345 kV lines that go out from our switch yard to distribute power across the various areas of the state. Yes, sir?
Do you think that like recent developments in fusion energy could change the effectivity of fission energy, or even like render it inferior or something?
Yes. Originally, when we started working on fusion technology, it took significantly more energy input than the yield it was creating. Mm-hmm. Now it's getting to the point where it's getting neutral, and they even think we'll start getting positive yields, you know, getting more energy out than we're creating here within the next few years. The hurdle right now to that technology is how do you capture it? So you can create the energy, but it's figuring out a way to capture it and turn it into useful, into a useful work.
Yeah.
So I think that technology will keep getting explored. I don't know how, it's hard to say. There could be some revolutionary step in it anytime in the near future that would change things. I think, though, to get to the point of being able to turn that into large-scale power production is probably the same, still several years away. So there's a lot of technologies out there, SMRs, fusion, other ideas out there, large-scale storage, electric storage, batteries, that concept.
Molten salt reactors or whatever that is.
Yeah, molten salt reactors, that's all part of the SMR designs. There's a lot of different technologies out there. None of it's on the horizon, in the near future. It's probably still a decade or better out until we start seeing that.
I'm the executive with the company Dominion Energy that's kind of in charge of everything that goes on here at the plant. So a lot of experience in commercial nuclear power. So I worked there's a bunch of different sites around the country that kind of supported that effort, and I worked at a bunch of those prior to coming to commercial nuclear power. So.
No way! Dude! Those are both reactors right here, PWRs. Pressurized water reactors. Take a look at that. Wow, take a look at that.
There's somewhere here, but the scale of the person is about this big in comparison.
That's amazing. Wait, actual radiation?
Yeah.
So that rotates the shield on the top, and that rotates the source on the bottom.
What?
And then that's... Yeah.
Gamma, beta, alpha.
So then,
that's so cool. Different kinds of radiation, different materials.
Wait,
where's lead? Is there a lead plate?
Fiesta-ware.
Oh my god. Dude, are those the control rods for the reactor? No way.
Come on in.
Holy. Dude, I'm gonna lose my mind out here. That's to the turbine.
So,
Yeah.
give you a solid idea here. There's a lot to talk about. So, everybody's obviously looking up here at the core mimic. So, each of those red lights would be one control rod, right? So, if something was going on at the plant, there was some kind of malfunction or event, the reactor protective system, which is those 4 panels over there, various plant parameters will cause 2 out of 4 of those to go into trip. If we get 2 out of 4, then the plant trips. These control rods all lose power and they drop into the core and shut it down. Here you look over here, this is a mimic of the reactor coolant system. So reactor in the middle, 4 reactor coolant pumps, and then the 2 steam generators. So like we talked about, that high pressure, high temperature water gets circulated through the steam generators, through a bunch of tubes, and then through that heat transfer process, steam is created on the secondary side, which if you look over here, you got the representation of the steam generators, right? They'll produce steam that goes through the main turbine and then is dumped into the condenser where it's condensed and then it's run through the cycle again. So over here, the secondary side, so this is all of the clean side, 3 condensate pumps, and then these are our steam-driven main feed pump, cooled. So when I do the demonstration later, you'll see this change dramatically. So this is the pressurizer. So this is basically like a, not really an expansion tank, but it's a tank that piped right off of one of the reactor hot legs. And this tank is heated up higher than the reactor coolant system, so it maintains pressure on it. Section here is chemical and volume control. So we have 3 charging pumps. Basically, we're always taking some water off of the reactor and running it through like resin beds and things like that to continuously clean it up. The more, say, corrosion products and things floating around in the water, the more radiation. The containment can handle up to 40 pounds pressure, so this massive building will get pressurized up to 40 pounds. And that's coming from a big old tank that's outside called reserve water storage tank. So those will push water in up to about 1,400 pounds. Like I said, that's if there's a break or something that brings pressure down in the primary. And then we have low pressure safety injection pumps. And these are that long-term core cooling that I was talking about with those pumps over there. These pumps will pump through those heat exchangers and help to cool the reactor.
See all the procedures, books, stuff. It's to refresh their knowledge on what's in the procedures, how to use the procedures, and the 3 tenets that we drive for the operators is keep the reactor covered, keep it cool, and control reactivity. You know, if pressure gets low, right, we use these systems to recover, to put water above the fuel to keep the core cool.
How come this row of buttons right here are covered?
So all of these buttons here are either initiation or block signals for our emergency safeguard signals. So you don't want somebody walking up and actually punching, say, an MSI button, which will cut steam off to the secondary plant, pressure will go high, trip the plant. So it's just human error kind of thing.
Are you capable of, have you ever trained for a black start? If you guys don't have, if the whole grid is down, can you start off and start pushing power when there's nothing to push against? And
Yeah,
get the grid going again?
Yes, we could.
Cool.
That's actually part of it. So it would literally take days if you had to go through something like that anywhere in the country.
And you have a normal day where everything is going hunky-dory, there's no problems. Are they sitting here just looking most of the time?
So Mark mentioned that. So we do normal, what we call surveillance testing. So a lot of the safety systems are being tested on a periodic, once a quarter test or something like that. So there'll be a mix of that. There'll be a mix of maintenance. So they'll do a lining of equipment to allow a pump or a valve to be taken out of service so we can go have maintenance done on it.
Yeah, so 2 very brief mechanical related questions. First one, I was wondering how the control rods were retracted. Is it with like a hydraulic mechanism, a geared mechanism? How exactly are they pulled out? Because they must be pretty heavy.
They're
grippers. So basically, and it varies plant to plant. Basically, there's a set of grippers that will grab the control rod and pull it up, and then another set will grab lower. These will let go, and then they'll grab again, and it's all.
It's coils.
Yeah,
Magnetic coils.
So it's kind of like a maglev, right? You got the electromagnets and
magnetic coils are
AC
what-
current.
So if you cut power to it, they all let go. It drops.
That's so cool. And second question, I'm not sure if I was just looking wrong, but I was noticing that the plant doesn't necessarily have a conventional cooling tower design. Like, it doesn't look like a Venturi. What kind of a cooling tower is it?
So we don't have a cooling tower.
There you, okay.
Long Island Sound is what we use.
Oh.
We pull in seawater to go through those condensers to cool the steam coming through the turbine, and then that's just discharged out the other
Got
side.
it. That makes sense, because I was looking for it. I'm like, where's the cooling tower?
With both units online at full power, we heat up the water that comes in about 18 to 20 degrees.
Got
So
it.
it comes in at 50 degrees, it's going out at 70 degrees.
And the reason we can do that is because the temperature of the Long Island Sound is cool enough that we don't need a cooling tower. Right, when you go to the Midwest and
Yeah.
you're off of a river, right, the river is very shallow, which you would need, a cooling tower type thing to dissipate that heat.
So what I was going to show is one of the pipes on the reactor coolant system. One of these pipes were to fall off the reactor coolant system, basically all the water in it would immediately flash to steam and blast into that containment building. And you'll see on the meters, the low meters at the bottom with the red numbers, that's containment pressure.
We'll take alarm to the operators here, they'll alert them what's happening.
No way.
So ready?
Oh, yeah.
That's my state of the art.
All right. This is...
So that's the loss of power.
Uh-oh.
Diesel generators coming back up to
Oh.
power the plant. Current relays that you just heard.
Oh, my God.
How do you focus with so many different alarms?
It's like Apollo 13.
First thing is the reactor. Verify that the reactor's tripped, make sure all the rods are in, power's lowering, and that.
Man.
Next is that the turbine tripped, because if the turbine hasn't tripped, it's going to be pulling steam off of the reactor and cooling it down too much. So the next is the turbine. And then after that, it's the electric plant, make sure we have power. So once we know we have power and we're good there, then we come over, we check these systems, because these are the pumps now that are providing cooling to all of that over there. And then next, pressure in the system, make sure that's coming back. Level, then pressure. Then they're going to check containment conditions and radiation monitors. This screen right here is what they look at for all the radiation monitors.
That's the longest range I've ever seen. Wow. This is a long one.
It's a 100-yard range, 2 tiers, top and bottom. All right, so we shoot from elevated, we shoot from bottom, we shoot prone, kneeling, sitting, standing. Local departments that come and use this, FBI SWAT uses it, state police SWAT uses it. A lot of local law enforcement come out and use it. One, because it's warm, right? You're not out in the cold all the time. More specifically, they like to come and use it so we can turn our lights on. All right, so they can get their night fire, their thermal training, night vision training, right? Instead of having to go out at midnight, they can just come in here during the day, we shut the lights on.
How? I just blocked myself in the head. Take a look.
Do it
at that.
360. So we can get a. Oh yeah. Oh yeah. There you go.
Oh, that's cool. Work. Oh my God, it works. Oh my, it's working. There you go. It's all focused. That's so cool.
Stimulate command debt, we would actually throw a flash. All right? So I'm going to throw it, you'll be able to feel the effects of it. All right? It doesn't have the flash portion. Okay? So you guys don't have to be afraid. All right? All right, so everybody go ahead and don those for me, please. Make sure they're all on. You guys ready?
Yep.
Frag out!
Whoa! That was cool.
One more?
Yeah! Another one!
You want the lights on or off for this one?
On, please. On.
On?
For the video.
Nope. All right, everybody got their eyes and ears?
Oh, yeah.
Frag out.
Woo!